Again, you start with your SRAM, and okay, I did not turn on the recording option. So, okay, it will be an issue. Anyway, not a problem. So this is your bit line. Okay. So you want to do the read operation, right? So let us assume that here is 0 is stored and at this node 1 is stored. So what will you do if that is the case? First thing, first step, pre-charge your BL and BL bar with 1. So that means I'll just have high voltages at this point. Then what I'll do? I'll make my word line to go 1. So that means what? This is on, this is on, these two transistors are on PG1 and PG2. And what can you say about your PU1, PU2, PD1 and PD2? So your this node I am seeing 1. So initially at this node I am seeing 1 and this node I am seeing 0. So for the this inverter, my this will be on, PD1 is on and PU1 is 0. Similarly for the right hand side inverter, what will happen? At the gate I see 0. So this will
PU2
be
on,
on, PU2
PD
will be on and this will be off.
off. Yes.
So this will be off, this will be off. And also you have 1 at this place. So in this right hand side, you see across this transistor between the drain and source, you see 1. So no current will flow. Can you see that?
Yes, sir.
Similarly, in the left hand side, you see that this potential is 0 and this is high. So a current will flow. So the current cannot go to this path because it will see the gate of the PU2 and PD2, cannot see this path because it's turned off. So this entire current will be dumped through the PD1 to the ground. So what will it lead to? It will lead to, for example, at this point, you have the capacitor connected. This is just for conceptualization. So basically, you can think as the capacitor is discharging. So the potential at BL will drop from 1. So this will drop. Is that clear?
Yes, sir.
So if the potential from 1 is dropped, so what you do next? You connect a sense amplifier, or for example, let's say an op-amp. So let's say this is minus, or let's say this is plus, this is minus. So the output, you sense the output. This is called sense amplifier. So you sense the output. So in this particular case, your negative terminal has 1, positive terminal has less than 1. So output will be negative. So this negative output signifies that at node 1 you have 0 stored and at node 2 you have 1 stored. So you have successfully read what is stored inside of the SRAM cell. If this sign is to be positive, then you could say that it is 1 and it is 0. So this is reading of the data that is already stored in the SRAM cell. Is that clear?
Yes.
So now we'll see the write operation. Okay, this line has come here. So write operation. So let's say you have 0 stored and 1 stored. So what you want? You want N1, you want to write 1 to N1 and 0 to N2. Write this in the SRAM cell. So what will you do? First thing, pre-charge BL and BL bar, BL to 1, BL bar to 0. So now this is charged to 1, this is to 0. Second stage, make your WL equal to word line equal to 1. That means this is on, this is on now. Fine. So now what will happen? So again the same thing. This is on, this is on, these are off. In this case, it is again seeing the same and it will charge up the n node because there will be some capacitor. For understanding, you can assume that there is some capacitor connected to these nodes where the charges are being stored. These are nothing but the input and output nodes, right? There will be the device's intrinsic capacitances. So that is what I have not mentioned, that how these are stored. These are stored at the capacitances at these two nodes. So the bits in SRAM cells are stored in form of charges. Okay. Okay. So if that is the case, then similarly, what is happening at the right hand side? This transistor is now on. So this one will get discharged through this node. So if you let the nodes to get discharged, depending upon the time constant, your N2 or your N1 will go from 0 to 1, and simultaneously your N2 will go from 1 to 0. So this is basically what you desired. So that is how you write to an SRAM cell. Okay, is that fine?
Yes,
So
sir.
if we move for the DRAMs, so DRAMs are very simple. So these are connected. This is your bit line. This is your word line. So if you want to write, so what if you want to hold? If you want to hold, you just make your WL equal to 0. That will disconnect this transistor or off this transistor. So whatever value you have at this node will should be intact, right? So this is called hold operation. But what is the catch here? The catch is that even at 0 VG, at 0 VG, I of is not equal to 0. So some leakage current will flow which will discharge this capacitance, right? Or decrease the value of the node. So that creates an issue. So that is why to store the value or to keep the value stored for a longer time, you need to keep refreshing or charging periodically your bit line so that your data can remain stored. Okay, so that is why it is called dynamic.
So, sir, my refreshing time should be greater than the discharge time, right?
Your refreshing time
Less than,
should be lower than the
yes, less than.
discharging time. Yes, that is what
Yes.
you do. There are technologies to do the refreshing of the or charging of the periodic charging of the bit lines.
Okay.
Okay, so now
Okay.
to write, what will you do? Make your WL 1. So your transistor will be 1. So whatever node will assume the value, whatever bit line is stored. So basically what you are doing, you making this on and you are charging the capacitance. And similarly, if bit line is 0, so if this is ground, what will it be? Your capacitor, whatever is stored, will get discharged through this transistor. So the node will follow the bit line value. So this is how you write in your DRAM cells. And how do you read? Again, the way you read is you make your WL equal to 1 and then connect some kind of sense amplifier to sense the what amount of voltage is there. But there is a catch that, for example, if you want to read 1, let's say this is what is connected. You have connected an sensor, and earlier the storage value is the stored value at the n is 1. So whenever you make your WL equal to 1, this transistor will be activated or it will be on. Then your this capacitor will start to also leak through this sensing path. So that is why your read operation, after read operation, value at n will get disturbed. Okay, so this is called destructive reading. So for every after every read operation, you need to compensate and again do the write operation or make sure C is charged or the value of node is there, uh, refurbished in that sense. Okay, so this is how your DRAM read, write, and hold operation works. So I think that is all I have for today. So if you do not have any question, all the best for your exams. And if you have any doubt regarding the course or for any help, you can email me at this.
Sir, you told that you will take up the FH calculation at the summary.
FH calculation, which part?
1 by 2 pi that are equivalent C in calculation how the equation comes
R
in the
equivalent
corner.
C. Okay, just let me see. So,
It is in the that prior week document, I guess.
so it is the same thing, right? This is we have covered in the last session. In the last session, we have mentioned that how your FH will come about. So it has nothing to do with your transistor for that matter, because you can break down your transistor to a small signal circuit. That will be nothing but your impedances, currents, control current sources and capacitances. So this FH comes from the same way that you calculate your open circuit and short circuit poles, right? This we have done. So that is why I have not shown it this time. I thought that it was covered.
Yes, yes, yes. It is.
So this is the same concept. You understand, right?
Okay, okay, sir.
The
Yes,
second
yes.
order system, how this FH, what will be R equivalent, open circuit and short circuit. In the same fashion, you can do for the transistors. Okay.
Okay, sir. No issue. Okay, sir.
So anything else in particular? So if not, I'll ask you to leave. So I have not recorded the session from the beginning. So I may need to revise the things what I have done just for the sake of recording. So you guys can leave.
Hello, sir.
Yeah.
I have a little bit question, but it is out of the context of today's. I
Okay.
just want to ask. I just want to ask you is that just recently Nobel Prize in Physics is distributed.
Right.
Could you please explain the a little bit about that? That how that Nobel Prize has distributed. Like the topic was on the subatomic particles uh, goes through the uh, uh, yeah, insulators. So could you please little bit? Uh,
So it is nothing but the tunneling. So I am not, see, I will not say that I will teach about or talk about the Josephson's junction and whatever is not that what they have. See, the quantum mechanical tunneling was a known concept. Fine. But what
okay.
these fellows have done, the Professor John Clark from UC Berkeley and other two professors from UCSB, Santa Barbara. So what they have done is that they demonstrated the entire quantum mechanical thing in the electrical circuits. Okay. So they claim that it is from a, see, for if I talk about one atom, so it is in a microscopic sense, right? So if I talk it in a circuit where they have shown around 10 to the power 9 copper atoms, if I am not mistaking, so they consider that as a microscopic or macroscopic sense of the quantum tunneling. So it is nothing, I have not exactly gone through the details of it, but I can tell you about tunneling if you, that is what you want to know, how the things go through the insulator. So do you want to know how current passes through insulators? You are not audible. Okay, so that I can tell you. Okay, your mic went off. Anyway, so what is tunneling basically? So you have idea of quantum, how much quantum mechanics do you know? So basically, if I write Schrodinger's equation, what Schrodinger equation tells me is that, so don't get afraid, okay? I'll just explain what this is. So this is your v of x times psi of x. So okay, I am taking one dimension, so I can use single. So equal to E of x. So what is this? This is your kinetic energy of the particle. This is what? No, this is not effective mass. This entire thing is your potential energy. And then this is your total energy. This is called TC, time independent Schrodinger equation. Okay. So now what you do, you solve this. This is basically a second order PDE where your psi of x is the wave function. So what is wave function? It is a probability wave. Okay. So it is just an abstract concept. Probability wave means, suppose I have some space. This is the x direction. So probability of finding electron at, let's say, x1, and probability of finding electron, let's say, at x2. This probability, if I plot, let's say this is p1, this is p2, and similarly, let's say for multiple position I plot it like this. So your psi of x is nothing but the probability wave. It will, if you plot p1, let's say you plot p2, let's say you plot p3, and so on with respect to x, it will see some curve. So this is known as your probability wave. So psi square basically gives the sense of probability of finding a particle in space. Okay. Now the question is, let's say I have a insulator. I have an insulator. So this is insulator. Let's say this is one metal. Let's say this is another metal. And potential at these points is zero. So y axis, what I am drawing is the potential energy. Okay. So if it is an insulator, and let's say one electron is passing from this, what will it see? It will see a huge barrier, right? So there are
Yes,
two
sir.
ways to go about it. One is that it acquires sufficient energy, pass over it, and then reach the other side. Fine.
Yes, sir.
Another way is to go through this. So
Yes, sir. Yes.
classically what you see? Classically you see that even if you have, let's say, this potential, for the time being, let me assume that these potentials are infinite, and this thing is called, something is known as potential well. So generally what you see, that these electrons will should be never be able to go, and it will just should
Yes,
be
sir.
just bounced back. But
Yes.
now if this is 0 and this is L and this dimension is L, and if you keep reducing your L, okay, so let's say to the scale of 1 to 2 nanometers. So you will see, if you plot this probability wave functions psi of x, you will see that after reaching this point, these electrons will decay through the probability of finding the electron will decay through the potential well, and you still have a non-zero probability of finding the electron in the insulator region. Okay, so this concept we call it as quantum mechanical tunneling. The same thing happens in your MOSFETs as well. For example, so far what we have studied is that your there is no DC current flowing through this region because we have an SiO2 layer. But if you
Yes, yes,
keep reducing this TOX down to 1 to 2 nanometer and below that, there is a non-zero current flowing through this. And the same thing you can consider like this. This you can consider as gate, you can consider as silicon, this you can consider as SiO2, and this will tunnel through. Okay. For example, this your NAND flash. For example, the circuit we have discussed, right? So your charges are trapped into this. So how do you think that this when it will get from stage 0 to 1, say stage 1 to 0, let's say we have a charge here of, let's say the state is 1, so it has charges inside it. So this is an insulator. To
yes, sir.
make it to go to 0, I need to get these charges move away from the insulator. How do I do that? How do I do this? I use the concept of gate induced drain leakage to get the charges tunnel through this oxide and pass through the drain. And then after some time, what will happen? There will be no charges, and the state in the 2D NAND flash or the transistor will be 0. So this is what your quantum mechanical tunneling is all about.
Yes, sir. Thank you so much,
Okay.
sir, for
Yeah.
this explanation.
Okay. So this may not be the exact thing what these fellows have shown, but tunneling is this. So at lower dimension in the nanometer range, your wave function or the probability of finding the electrons will not be 0.
Yes, sir. Now I get the better idea of it.
Okay. So you guys can leave if you do not have any question. I'll just go through the lecture once
Okay.
again just for the recording sake.
Thank you, sir.
Yeah.
Can you sir, just share in future? Can you just share that which classes will take so that if needed we can
So I
involve.
am not sure. So you can go to my YouTube channel. So if I take anything, it will get posted on that.
Okay, okay. Sir. No,
Okay.
I'm saying there is a live class. I'm saying.
Okay. Live classes. See, this happens in a lottery system. Okay.
Okay,
So there are PMRF scholars across India. So what they do, NPTEL people asks us to fill the choices that which courses we want to teach or be tutor in. So we fill out our choices and accordingly we are getting allocated. So I cannot comment at this moment. Maybe if I get selected for the next cycle, or if the professor does not have any preference for the courses that I'll apply for, then it will get updated. So another way you can check, uh, okay, just a minute. Another way you can check is, so if I share my screen, so is the screen shared?
yes,
Yes, sir.
So you can just go to my website and there in the teaching tab you will get updated here. Okay. So these ongoing things you can check it around January. If I take any courses, it will be there. And all the links and all what are the contents and all you can see here. Okay.
okay, okay, sir.
Okay.
Thank you, sir. Thank you for
Yeah.
this whole session. Okay,
Yeah. Thank you.
Thank you, sir, for throughout the course, your guidance.
Thank you. So let me just quickly brief because I did not record the session fully. So what we did today was that we started with this XOR thing. So okay, so we started with this XOR uh, implementation for that sake. So it was asked that an XOR gate is to be realized using two input NAND gates. The minimum number of gates required is this. So you can see that their options are 2, 3, 4, and 5. So we started with option 2, and we have noted that De Morgan's law will play an important role in designing this from the very first thing that we note that. And then we started using breaking the entire logic using De Morgan's law. So you can see that I have broken down that a bar b and a b bar to two functions of the form f1 and f2, and then from f1 and f2 we started with further designing f1 and f2 with respect to two input NAND gates. Fine. So we then we have decided that n equal to 2 is not possible because already one is taken by this f1 and f2. So we move to n equal to 3, where f1 and f2 with respect to two input NAND gates we started to design. So one two input NAND gate we have assigned for f1, another should be obviously assigned for f2. Then while designing the f2 or breaking down the f1 expression, we have seen that we need at least two NAND gates to design the f1. Similarly, two NAND gates to design the f2. So ideally we should have had 2 plus 2 plus 1, 5. But however, we have observed that AB bar and AB bar are common in this both two, so we can utilize that output. So the total number had boiled down to 4, the minimum number of two input NAND gates that were required. So this is what is the design we came up with, right? And also I have mentioned to the students that in case of your complex logics, in some such sophisticated algorithms such as Quinn-McCluskey and all are generally used to decompose the expression into a sum of products or product of sum based upon the design requirement. Then we have studied on the this pass transistor logic. So we have noted that multiple combination of A and B, and we have noted that this logic will come out to be an XOR operation, right? And transmission gate logic I have emphasized upon by noting them down that I have put the case that where I remove this bar and ask them to write the truth table. So some of them are able to tell so, but if you can see that this B bar and B or the gate inputs in the pass gate transistor should be in complementary nature. And this is well understood in the concept of transmission gate when you read it. So it is suggested, I have suggested that you guys should read that. Okay. So next problem was a delatch problem. So we have discussed that delatch, the working of delatch, that transparency means that Q will be equal to D when the clock is high. That means when it is level triggered, right? And the zero propagation delay and etc. So in the figure, the clock signal has a 50% duty cycle. That clock 2 is a shifted version, so it will also have 50% duty cycle. Then we try to draw the output characteristics. We have noted that during when clock 2 will be on, then only it will follow the Q value. So it is following the Q value. But we want to calculate the duty cycle of the output. So we are interested with the on portion of the output. So that is this portion. So I've noted that this is also moving with the same period of T clock. So the T on period is T clock 2 by T clock 3. T clock 2 we have noted down from the fact that it has a 50% duty cycle, right? So then it is T clock by 6. Then at the DC point we have calculated that it is 16.67% the duty cycle. And then we started discussing the memories. So DRAM, SRAM are the types of memories. Which kind of memory? So I've asked the student to what is DRAM, what is SRAM and SSD. So what is dynamic and static has been discussed. The node at which the bits are stored needs periodic refresh. Static means we do not need that. Random access means each and every bits you can access randomly. So this is the same thing by choosing randomly from a bucket of 12 apples. You get to choose one. So that is how the random access works. And then we discussed about your what is volatile memories, what is main memory. Volatile memories is power supply is off and data is erased. Non-volatile memories is it holds the data even when your power supply is off. So the first option seems correct. Then we have discussed memory hierarchy, the reason behind it, SRAMs and DRAMs. So the memory hierarchy, we have discussed that we have first unboxed, we have first broken down the laptop processor. So it will have CPU, main memory, SSD. SSD is the non-volatile memory of in your computer. So CPU will have two component, ALU and CU. So we have noted that this is a von Neumann architecture. Then we need to wait before fetching the data from memory. This is an artifact of the von Neumann architecture. Then we have broken down the memories into multiple levels. We have shown them what is cache, what is main memory, what is SSD, what is HDD, right? And what are the typical values of it. Then why cache has been broken down into three levels. This is to do with the multiple core operation of the CPU, where we cannot increase my F clock to increase the speed of the processor because it will lead to a gigantic increase in my dynamic power. And that is why this cache memory is divided into three parts. Mostly I have shown them with my in my computer that where is the, how can you see the memories and where can you see the memories, right? And how much is it? Then we have shown them the relationship between speed and size of the memory. So if you go from top to bottom in the memory hierarchy, your speed decreases and your memory capacity increases. This is to do with the area of the transistor, because to have higher speed you need to have higher ion. That means you need to have a larger width of the device or the transistor, so memory density will obviously fall. And also I have emphasized upon the requirement of memory, very dense memories in these days because of your AI, ML, and big data kind of stuff that is going around. And also you need to have multiple storage class memories to which are making place into this memory hierarchy. Primarily because you are deviating from your von Neumann architecture to something called in-memory computing. Then we have told the students that in the CPU companies are the one who designs the SRAMs because that are with on the same chip as of CPU. And we have discussed on some of the DRAM companies. Then we have shown them the memory array architecture. Then we have memory sizing, area efficiency. We have shown them how a DRAM cell sits at the memory crossbar and how the what will be the size of the crossbar, etc. Array efficiency we have discussed on emphasized upon because it holds a very important place in designing the evaluating the designs of the new technologies or new memory architectures. Then we have discussed your DRAM's sizing of the transistors. So we have mentioned that DRAM has a size of around 6F square. F is the minimum feature size of the particular technology. Then we have discussed on SRAMs. We have discussed the structure of the 60 SRAM and the tentative size of that. We have discussed on 2D NAND flash, and I have also pointed out to them that to follow the branch education channel on YouTube so that they can get a more pictorial view of it. Then we have started discussing with the SRAM hold, read, and write operations. So in the hold operation, we have mentioned that if you need to just place your WL equal to 0, the pass transistors will get off, and your storage will be happen at the N1 and N2 node by a fashion of cross-coupled inverters. So this is obviously static because it does not need any refreshing of any sort of the nodes. And also we have discussed that if they are interested, they can look into the butterfly curves of the SRAM hold operation and so forth. And then we have started with the read operations. In read operations, we need to pre-charge the bit lines both to 1. And then what we do, then we just connect your WL to 1, and you can see that in this case, PU1 and PD2 will get off because earlier I have assumed that at N1 node we had 0 and at N2 node we had 1. So this bit line will get discharged through the PD1 transistor, and this will not have any effect. That means at your bit line bar you will have 1, and at bit line you have a lower value than 1. So you can just sense the sign of the different, you can take a difference and sense the sign. That will give you the idea about at which node is holding what value, right? So your N1 will have a 0 value if this is negative, the way we have connected the sense amplifier or the op-amp. And so moving on, we have started with the write operation. I think beyond this, the recording I have started. So yeah, that is all. We have discussed write operation of the SRAM. Then DRAMs, we have discussed hold, read, and write operations. And yeah, if they have any question, they can ask or email me at this. So all the best to the students for the exam. So the course ends here.